Hello friends, welcome to the course Essentials of Data Science with R Software 1, in which we are trying to understand the basic concepts of probability theory and statistical inference. And I hope now the lectures are going to be more interesting, because we are moving towards the real application, that how the things are being obtained. Okay, so now you can recall that in the last lecture we had talked about the methods of estimation, and we had considered the method of movements. Now, exactly on the same lines, whatever I had explained you, that what is called the estimation of parameters, same thing is valid for this lecture also. In the last lecture you had used a philosophy that was based on the movements, so you had devised the method of movements. Now, in this lecture we are going to devise one more idea, one more philosophy to estimate the parameters, and that is based on maximum likelihood. And after this I will try to give you a small result which is called as Rao-Blackwell theorem, that will help you in obtaining some good estimators. Okay, so first let me try to give you an idea that what are these maximum likelihood estimators. So let me try to give you a very real life simple situation where you are trying to take decisions in a day-to-day life. Now tell me one thing, we have a situation that you have to go from your home to, say, railway station, and suppose railway station is 5 kilometers away, and this is the time for the office hours. So means you have to go around 5 or 6 o'clock, and suppose you have just 1 hour left for your train to catch. So now suppose your train is at 6 o'clock, and at 5 o'clock you are at home and you want to reach the station in time. So now you have couple of options by which you can go. One is by walking, second is by using a cycle, third is using some auto rickshaw, fourth here is using a taxi like a car, or fifth here is means you just try to run. Which of the method you are going to use? Now remember one thing, this is the traffic time and you have to pass through with a heavily traffic loaded road, right. Now you try to take a pause and try to think about it, but my question is, you can tell me the answer in within fraction of second, but my question is that what are you doing inside your brain because of which you are trying to take such a decision? Try to take a pause and try to think about it, and if you cannot think, just try to start the video once again. So now what are you trying to do? You have couple of options, say walking, run, say auto rickshaw, simple rickshaw, cycle, taxi, car, etc. And now your brain starts computing the probability of an event, that what is the probability that if you go by this mode of transportation, then you will reach to the station, say, within 1 hour. And you try to compute such probabilities for all the events, and you try to take care of all the possibilities. Means there can be traffic can be high, there can be some traffic jam also near stations, the traffic is usually pretty high, and you are going in the, say, about 5 o'clock in the evening, so the traffic is definitely going to be higher. Now you tell me what you have done. When I started the course, you always felt that the computation of probability is very difficult, but now ask yourself and tell me, you have computed the probability of such a complicated event very easily in a fraction of a second. So how can you say that you don't know statistics and you don't know how to compute the probability? So now let us try to understand what you have done. You have taken, suppose in order to make it more simple, suppose I consider here 3 options: walking, taking a simple auto rickshaw, that is a 3-wheeler, and try to take a car. Now try to calculate what is the probability that if you walk you will reach in time. Well, you have to walk 5-6 kilometers with your luggage, so the probability will be say 20%, suppose. Now in case if you try to take an auto rickshaw, that they are the 3-wheelers, they are small, they can go through here and there very easily, and if there is a traffic jam, possibly they can take a different route and they can take some small narrow road and they will make you reach to the station. So, the probability to reach the station is going to be something like 80%, 90%, and then the third option is you take your car. Somebody will drop you using your personal car. Now, with the personal car, if there is a traffic jam, you just cannot do anything. If there is a traffic, the speed of the car is going to be extremely slow with the risk of traffic jam. So, the probability that you will reach by your own car, that is also say 40%, 50%. Well, these numbers are just hypothetical, just to illustrate you. Otherwise, you yourself can compute such probability depending on the conditions. So, now if you try to see, what are you trying to see? You have here 3 probabilities, 20%, say 80% and say 50%. You try to choose the whichever has got the maximum probability, and then corresponding to that you try to see what is the mode of transportation by which the probability is maximum that you can reach. That is your auto rickshaw in the given time frame. So, what you have done? You have obtained a sample of observations and then you have computed the joint probability of all those observations, and then you have maximized the probability, and then whatever is the value of the parameter corresponding to the maximum probability, that you are trying to say this is the most probable value. What is that? This is maximum likelihood estimator. So, now I have given you an example where I should be 100% confident that you know the maximum likelihood estimation. The only thing is you didn't know the name. You knew how to compute it, but you didn't know what exactly you are trying to do mathematically. So, that is my objective in this lecture, and let us try to begin this lecture and try to understand what is this method of maximum likelihood to estimate the unknown parameters on the basis of given sample of data. Okay, so now let us come back to our slides and try to begin the lecture. Okay. So, one of the best methods of obtaining a point estimator of a parameter is the method of maximum likelihood. This technique was developed sometimes in 1920s by Sir R.A. Fisher, who is said to be the father of the statistics. Right, as the name implies, the estimator will be the value of the parameter that maximize the likelihood function. What is the likelihood function? Likelihood function is nothing but the joint probability function, and you know how to compute the joint probability function either in the case of discrete or continuous random variable, as simple as that. So, likelihood function is simply a name or an alternative name for the joint probability function, right. And when I am trying to say the likelihood function, usually we do not discriminate between the probability mass function or the probability density function. Whatever is the joint function, in the case of discrete, that is going to be joint probability mass function, and in the case of continuous it is going to be joint probability density function, that we try to consider as likelihood function, right. So, first let us try to understand what are the steps that are involved. Well, there can be different steps depending on the problem, but I will try my best to give you a couple of examples so that I can satisfy you. So, basically what are you trying to do? You are simply trying to maximize the probability, and you are trying to find out the value of the theta corresponding to which, given the sample, the probability is going to be the maximum, right. So, let x1, x2, xn be a random sample from some probability density function or probability mass function, say fx theta, and we try to write down here as say f of x given theta, because theta here is fixed and we are trying to find out the value of theta for a given value of x1, x2, xn, the observed sample space, and we assume that theta belongs to capital theta, and capital theta is the parametric space. Now, you know this is a random sample, so the observations are independent. So, the joint distribution of x1, x2, xn can be written here as like this, f of x1, x2, xn given theta. This is simply the product of their marginal densities or their product of their individual PDFs, and this is in general indicated by L theta x1, x2, xn, right. So, here we have used the property of independence, and that you know that two random variables are independent if their joint density function f x y can be expressed as the marginal density function of x and y, that is fx into fy. So, that is the rule which we have used here, and now this L in general is going to indicate our joint probability density function, which is now called as likelihood function. So, likelihood function is a function of theta given the observed and known sample values x1, x2, xn, which is the joint probability in case of a discrete random variable, like as probability of capital X1 equal to x1, capital X2 equal to small x2, and capital Xn is equal to small xn, right, just like the same concept that you studied earlier. Now, based on this likelihood function, we have to find the value of theta which is likely to maximize the probability in a sample, and the sample is given to us. So, the maximum likelihood estimator, which is abbreviated as MLE, M from maximum, L from likelihood, E from estimator. The MLE of theta is the value of theta that maximizes the likelihood function, as simple as that, right. And in case if you are trying to consider the discrete case, the maximum likelihood estimator is an estimator that maximizes the probability of occurrence of the sample values x1, x2, xn. So, this can be written here as a probability that x1 equal to x1, x2 equal to x2, and xn equal to small xn, right, the usual approach of writing the joint probability. Now, x1, x2, xn are now obtained, they are now given. Now, you simply try to find out the value of theta, say as theta hat. Now, the value of the likelihood function at theta equal to theta hat is always going to be greater than the value of the likelihood function at theta for all theta belonging to the parametric space theta, because you are trying to maximize the likelihood function, you are trying to maximize the probability of observing this sample from a given population whose parameter is theta. So, definitely the likelihood function is going to be the highest at the point of maximum likelihood estimator, right. And after that you simply have to solve it and you will get the maximum likelihood estimator. Well, when we try to estimate it on the basis of given sample of data, then yeah, different types of things are coming into picture, and I will try to explain you with some examples, right. So, the first example I take here, where I am considering the sample x1, x2, xn from a Bernoulli distribution. This is a random sample, and the parameter here is p, whose probability mass function is given by this one, right. So, your x1, x2, xn, they are IID. So, the likelihood function can be written here as say as the joint probability of x1, x2, xn, like this one, and yeah, it is just indicated by here L for the sake of simplicity in writing again and again. So, now this probability function can be written as a product of this probability density function for xi's. Now, in case if you try to simply solve it, this will come out to be like this: p raised to the power of summation xi into 1 minus p raised to the power of n minus summation xi, right. So, the maximum likelihood estimator MLE p is the value of p that maximizes the likelihood function, this one, which is now here. Now, the next question is, how are you going to maximize it? Now, the optimization techniques now come into picture. In case if the likelihood function is complicated, you can use any numerical technique to maximize it. You can use different types of algorithm in case of any complicated function, and so on. So, now once you obtain the value of here p from this function which is maximizing this function, there is a reason for me to be happy that I have got the maximum likelihood estimate of p. Now, how to maximize it? That is not the question which is answered in statistics. For that, you have to take the help of mathematics and optimization theory. So, in this particular case, we are simply going to use the principle of maxima and minima, and many times we will try to transform the likelihood function in some suitable way, for example log function, because both are monotonic functions, right. So, in case if you try to find out the maximum from the L, then the same maximum can also be obtained by maximizing the log of L. And in case if you try to understand this concept from these two figures, so you can see here that here we have plotted the likelihood function as a function of p. We have simply plotted here the L for different values of the parameters and their probabilities. Now, we try to take the log of this likelihood function and we try to find out their different values, and we try to plot it on the same scale. You can see here this scale and this scale, they are the same, right, and the curve will here look like this. But in both the cases you can see here that the point at which it is reaching the maximum is here the same, that is 0.6 and 0.6. So either you try to maximize this figure or this figure, that will not make much difference, or that will actually not make any difference, right. Once you are trying to use any numerical technique, optimization theory for some complicated function, it may be possible that different algorithms may give you different values, but those values are not going to be much different, and they will be dependent value. That is what I was trying to say. So now in this case, we simply try to use the principle of maxima minima, and we try to take here the log and we try to maximize it. So in case if you try to take here the log, it will come out to be here like this, summation xi into log of p into n minus summation xi log of 1 minus p. And if you try to simply differentiate it with respect to the parameter, it will here be like this, and then whatever is this equation, that is substituted to 0. So this equation, when we are trying to equate it first derivative or any derivative of the likelihood function or the log likelihood function to 0, this is usually termed as likelihood equation. Well, in case if there are more than one parameter, say 2 parameters, then you have to differentiate the likelihood function with respect to each of the parameter, then there are going to be 2 likelihood equations, right. So now in case if you simply try to differentiate it, put it equal to here 0, you obtain here p is equal to x bar, and this implies that p hat is simply equal to here the sample mean, like this one. Now the next question is how to know whether this value is going to give us the maximum or minimum. So in case if you try to substitute p equal to x bar in the second derivative of the log likelihood, then this term will come out to be negative. That you can verify, that's a very simple thing. So you can see here now the sample mean is the maximum likelihood estimator of the population proportion in case of Bernoulli distribution. So that means in case if you don't know the value of p, you have obtained a value, you have obtained some values in the sample, simply try to find out their arithmetic mean, and the values are going to be in terms of 0 and 1. So the arithmetic mean will give you the value of, or the estimated value of the population proportion. Right. Now let me try to take here one more example where this principle of maxima and minima is not going to work. So let x1, x2, xn be a random sample from a uniform distribution whose the parameters are 1 and theta. So the PDF here is given here like this, fx is equal to 1 upon theta when x is lying between 0 and theta and 0 otherwise. Now in this case all x1, x2, xn, they are IIDs. So the likelihood function can be obtained just by multiplying individual probability density function. So you simply have to write down here like this, and this will become here 1 upon theta into 1 upon theta into 1 upon theta n times, right. So the likelihood function will come out to be here like this, 1 upon theta is power of here n when x is lying between 0 and theta and 0 otherwise. Now as per the rules of the maximum likelihood estimation, the maximum likelihood estimator MLE of theta is the value of theta that maximizes the likelihood function, this L. Now in case if you try to employ here the principle of maxima minimum, then it will actually fail, right. This will not give you any result. But this is not the problem of likelihood function. These are the mathematical things that you have to choose an appropriate method to maximize the function. So in case if the method of differentiation fails here to finding out theta, it does not mean that the MLE does not exist. So now in case if you try to look at this function 1 upon theta and this here range, you can see here you have here the observation x1, x2, xn. So what we try to do here, that we try to arrange them in some order. So all this x1, x2, xn, they are going to lie between 0 and theta, and that is what I am trying to do here, that you have here the function 1 upon theta is power of here n, and now you are trying to order those observation here as say the x1 less than x2 up to here less than xn, and all of them are going to be lie in the range 0 to theta. So what is the meaning of this? Suppose I have here x1 equal to suppose 5, x2 equal to here 3 and x3 equal to here suppose here 6. So now you can see here whatever is the minimum value out of them, this is here 3 and then here we have here 5 and then we have here 6. So we try to denote this minimum value as the say x, and inside the parenthesis we write the 1 in the subscript, and then this here x2 in the same way for indicating the value of 5, and x3, that means 3 inside the parenthesis in the subscript. So, these are the values of x1, x2, x3 that we are trying to indicate. So, you can see here that here this x1 inside the parenthesis where I have written 1, this is same as here x2, and this x2 where I have written the 2 inside the parenthesis in the subscript, this is here same as here x1, and this x3, this is here same as here x3. So, you can see here these x1, x2, x3 in which I have written the 1, 2, 3 inside the parenthesis, they are the ordered value, right. That means the x1, x2, x3 are the original observation. They are arranged in some increasing or decreasing order, and x1, x2, x3 when I am trying to write down 1, 2, 3 inside the parenthesis in the subscript, then these are the ordered values. So, we try to arrange the sample values in this order. So, all the sample values x1, x2, xn can be written like this, and they will be lying between 0 and theta, because every xi is lying between 0 and theta. And now, you have to observe under what type of condition this 1 upon theta raised power of n function is going to take the maximum value, right. So, one thing you have to just notice that this is actually called as ordered statistics, and means if I am writing here like this x and then I inside the parenthesis in the subscript, this is the ith ordered value, and yeah, this x1, this will simply be the minimum value out of x1, x2, xn, and x, and here that will be the maximum value of x1, x2, xn. So, now you can see here your likelihood function is 1 upon theta raised power of here n. So, now each of this ordered value is going to lie between 0 and theta. So, I can say that theta is going to take the minimum value when theta is greater than or equal to maximum of x1, x2, xn, which is the nth order statistics, right. So, now you are going to maximize it. So, theta is minimum when theta is equal to xn. So, what we want? We want the likelihood function to be maximum, and our likelihood function is in the form of 1 upon theta. So, obviously, in case if you try to take here theta is equal to xn, this likelihood function is going to be maximized, and that is why I can say that xn, which is the maximum value of the sample values x1, x2, xn, is the maximum likelihood estimator of theta, right. So, you can see here you are trying to observe the form of the function of likelihood function, and then you are trying to find out the value of theta which is going to maximizing it. Now, similarly, if I try to take here one more example where x1, x2, xn, they are coming from an exponential distribution with parameter lambda, then x has got this PDF, and now we have to estimate the lambda using the method of maximum likelihood. So, we try to obtain here the likelihood function exactly in the same way. We try to multiply the individual PDFs and we obtain this function. So, this is going to be your here L, right. Now, you can see here that in case if you try to take here the natural log and you try to differentiate it, then it is easier to implement the principle of maxima and minima. So, we try to differentiate this log of L with respect to the lambda, and we get here this type of equation, n upon lambda minus summation I goes from 1 to n xi, and I try to substitute it to 0. So, this will give us the likelihood equation. And now, if you try to solve this equation, you will get here say lambda equal to 1 upon x bar, and this is going to indicate that lambda hat is equal to 1 upon x bar, and this lambda hat is going to be the maximum likelihood estimator of lambda. But we need to ensure that this is the value of lambda which is really going to maximize the likelihood function, and for that we simply try to check the second order derivative condition of the principle of maxima and minima, and this inform us yes we are correct, and lambda hat equal to 1 upon x bar, that is 1 upon sample mean, is the maximum likelihood estimator of lambda for the exponential distribution, right. Now, in case if you want to compute this value on the basis of R software, this is 1 upon here mean, that is all, right. And similarly, if I try to take here one more example from the normal population with mean mu and sigma square. So, we have got this sample from this population, and the PDF is given here by this fx 1 upon sigma root 2 pi exponential of minus 1 upon 2 x minus mu whole square upon sigma square. Now, I try to write down here the likelihood function just by multiplying all the PDFs for x1, x2, xn, and this function can be obtained here like this. Now, you know that by looking at the form of this function, it is easier to take the log and then apply the principle of maxima minima. So, I try to take here a log of this likelihood function, which comes out to be here like this, and then I try to differentiate this log of L with respect to mu and sigma square, and we obtain here two likelihood equations, right. And now, once they are there, just solving them, we can obtain here that mu hat is equal to x bar and sigma square hat is equal to 1 upon n summation I goes from 1 to n x I minus x bar whole square, right. So, these are the maximum likelihood estimates of mu and sigma square, right. And in case if you want to check whether these values are going to provide the maximum of the likelihood function or not, then we have to check whether this matrix is a negative definite matrix or not at mu equal to mu hat and sigma square equal to sigma square hat, and that can be verified that it is coming out to be true. And after that, we are sure that mu hat is equal to x bar and sigma square equal to 1 upon n summation I goes from 1 to n x I minus x bar are the MLEs of mu and sigma square respectively. So, now in case if you ask me that how to calculate this thing, then I know that this x bar can be computed by mean, and this variance 1 upon n summation x I minus x bar whole square can be obtained by this expression n minus 1 upon n into variance of that data vector, right. So, now that we already have done when we were trying to discuss about the basics of the R software. Now, one thing before I move forward, if you try to see here this x bar, this is going to be uniformly minimum variance and by estimator of mu that we will do, that we can show, but this estimator of sigma square is not going to be the uniformly minimum variance and by estimator, and that is clear here. At least I know this is not unbiased, right. Expected value of sigma square hat MLE is not equal to sigma square, right. Well, these things are possible, nothing to surprise. Okay. Now, I have taken a couple of examples to explain you, and the moral of the story is that you simply have to write down the likelihood function and then you have to just optimize it. You have to find out the maximum value. So, how to do it, that now depends on you. You have a good knowledge of mathematics, now you know lots of optimization technique, numerical technique, you can use any one of them. And in the R software also there are couple of commands, but I am not going into that detail, but because my objective here is to give you the basic fundamentals, right. Computation is very easy for you. So, now some results and some properties of this MLEs. So, first important property is MLE is a function of sufficient statistics. You can always see, you have seen that say sample mean you have already proved that this is a sufficient statistics, and you are obtaining the sample mean to estimate the population mean in the case of normal population, right. So, and the second thing is this, usually we look at the maximization of the log of likelihood function, maximization of likelihood function with respect to theta and log of likelihood function with respect to theta, they are going to give you the same value, right. And third property is if theta hat is the MLE of theta, then any function of theta hat, say g of theta hat is the MLE of g theta, provided g theta is some single valued function of theta. So, this is called as invariance property of maximum likelihood estimates, and this helps us a lot in finding out the different types of estimator for different parameters of from the same population, right. Now, let me try to give you a quick idea about the Rao-Blackwell theorem, because this is going to help us in obtaining a minimum variance unbiased estimator of a parameter, right. So, that is a very simple thing. One thing you have to keep in mind, the statement of the theorem may not give you a real idea that how are you going to obtain the minimum variance unbiased estimator, but as soon as I try to give you the working rules, then the life will become very simple, right. So, now let me give you this idea quickly. So, let x1, x2, xn be a random sample from some distribution f x theta, where theta belongs to capital theta, and suppose delta x is an unbiased estimator of some parametric function g theta, and suppose capital T is a sufficient statistics for theta. Right. Now, we are trying to define a new statistics eta t, and this is defined as expected value of delta x given t equal to t. Now, since you have already assumed that capital T is a sufficient statistics for theta, so by the definition of sufficient statistics, we can say that this eta t is going to be independent of theta. Yes, if you have forgotten it, just go back and try to look into the definition of a sufficient statistics. Well, we had done two things, definition and the factorization theorem, but now I am asking you to look into the definition. So, now I can say here this, that eta t is a statistic, right. So, now in case if you try to look at the properties of this eta t, so for about unbiasedness, you can see here expected value of eta t. If you try to find out the expected value here, this will come out to be same as g theta. So, this eta t is an unbiased estimator of g theta, and here I have used the rules which you understood, that conditional, unconditional expectation of a variable, right. And now, in case if I try to find out the variance of eta t, under what type of condition it is going to be smaller than the variance of other estimator delta. So, this inequality, that variance of eta t is going to be smaller than or equal to variance of delta x with equality if and only if eta t is equal to delta x with probability 1. So, that means if you try to create a statistics with this formulation, that will always have a smaller variance than the delta x. And if you try to see what you have done here, you had one estimator delta x, and based on that you are trying to create another estimator here et using delta x. So, now this is going to give you a smaller variance if and only if eta t is equal to delta x, right. This eta t is called as a raw Blackwellized version of delta x. So, we are trying to consider an estimator, and then we try to convert it and we try to transform it, and this transformation is going to be done by a certain rule, and this will give us a statistics that is called as a raw Blackwellized version of the original estimator. And the application of this raw Blackwell theorem comes in conjunction with sufficiency, right. So, now I try to give you here some rules which are going to make your life very simple, that instead of doing all these things, you have to do very simple thing, and then you will get here a minimum variance unbiased estimator. So, for example, the first step is, suppose the setup is like this, that x1, x2, xn is a random sample from some distribution f x theta, theta belongs to theta, and g theta is the parametric function that we want to estimate. Now, the first step is simply make a guess about some unbiased estimator of g theta. That is not difficult, I am promising you, and you try to just have it. For example, if you ask me if I have to estimate the population mean from a normal mu sigma square, possibly I can say, okay, let me start with summation xi. I try to find out here the expectation value of summation xi, and it comes out to be here n upon mu. So, now I want to estimate here mu, so I can write down here summation xi divided by here n, this is equal to here mu. So, now this x bar becomes an unbiased estimator of mu. So, this type of exercise that we try to do. So, finally, we have here an estimator of g theta. So, let this delta x is an unbiased estimator of g theta. Now, find a sufficient statistics t for theta, that you have to simply use the Neyman-Fisher factorization theorem, and now improve on this function to obtain an unbiased estimator of g theta. Simply try to find out sufficient statistics and try to convert it into an unbiased estimator of g theta, and it has got minimum variance, and we get the minimum variance unbiased estimator, but this may not be unique, right. For uniqueness, we need here one more concept, this is called as completeness. The concept of completeness is needed to get a unique estimator. And now what we have to do, we have to first understand the concept of completeness, but definitely I am not going into detail because this will require some more concept which we have not done here, like as convergence almost surely, but still just for the sake of completeness of the lecture I am trying to give you here the definition of the completeness only. So, completeness ensures the uniqueness of estimators, right. So, now if I say that let there be a random variable x of either continuous or discrete, whatever you want, having a proper PDF or probability mass function, and that is a member of the family, say hx theta, theta belongs to omega, where omega is the parametric space. Now, if the condition expected value of Tx equal to 0 for every theta belonging to omega requires that Tx be 0 except on a set of point that has probability 0 for each hx theta, theta belong to omega, then the family, this hx theta, theta belonging to omega is called a complete family of probability density or probability mass functions. But anyway, I am not going into these details, and now I come to our business. That let me try to take here some examples and try to show you that how easy it is to find the minimum variance and by estimator, right. So, the first example is let x1, x2, xn be a random sample from a normal population with mean mu and variance 1, and then you try to find out a sufficient statistics for mu that we already have found. This was summation xi. Now, you try to ensure that this is also a complete statistics, although I am not doing it here, but you can believe on me that this summation xi is a complete and sufficient statistics for mu, right. Now, you simply try to take its expectation and try to convert it into an unbiased estimator of mu. So, if you try to take here expected value of t, this will come out to be summation of expected value of xi, which is here n times mu, and if you try to bring this n here, then you can write down here that expected value of t upon n is mu. So, this implies that t upon n is actually sample mean x bar. This is an unbiased estimator of mu. This is a function of complete and sufficient statistics. So, sample mean is the uniformly minimum variance unbiased estimator of mu, right. So, you can see here it was extremely simple to obtain the uniformly minimum variance unbiased estimator. Now, in case if you suppose want to find out the uniformly minimum variance unbiased estimator of mu square in the same setup, what we try to do here, that we try to find out the expected value of x bar square, which is variance of x bar plus expected value of x bar whole square. So, because here the variance is given here as a 1, so this variance of x is 1 upon n and expected value x bar here is mu. So, this becomes here 1 upon n plus mu square, and you want an unbiased estimator of this mu square. So, in case if you try to bring this 1 upon n on the left hand side, I can write down here that expected value of x bar square minus 1 upon n, which is mu square. So, I can now say that x bar square minus 1 is an unbiased estimator of mu square, and x bar square minus 1 upon n is a function of complete and sufficient statistics, because you already have proved that x bar is a complete and sufficient statistics for mu. And so, I can say that x bar square minus 1 upon n is the uniformly minimum variance unbiased estimator for mu square. You can see that how it is, right. Okay. Now, let me try to take here one more example, that suppose x1, x2, xn is a random sample from normal with mean 0 and variance sigma square is unknown, and we want to find out UMVUE of sigma square. So, now I try to use here a result that we have used many times from the properties of chi-square distribution, that summation xi square upon sigma square, this follows a chi-square distribution with a small n degrees of freedom. And you know that the expected value of a chi-square random variable is the same as the degree of freedom, and its variance is actually twice of n. But anyway, I try to use here this expectation. The expected value of this chi-square variable is equal to its degrees of freedom n. So, I can now write down here like this, that sigma square goes here and comes here, and I can write down here summation xi square upon n. Its expected value is now same as sigma square, right. So, I can say here that this quantity is an unbiased estimator of sigma square, and summation xi square upon n is a function of complete and sufficient statistics. So, this statistics is the uniformly minimum variance unbiased estimator of sigma square, right. So, you can see here it was pretty simple to obtain such estimators, right. So, now we come to an end to this lecture, and I hope you enjoyed this lecture, because you see right from the beginning our objective was to estimate the unknown parameters, and to reach to this point we had to understand the basic fundamentals of probability theory and other things. Otherwise, how can you understand, how can you find? Means I have given you, for example, say here mu square in the case of normal mu 1, but if somebody asks what will be the UV of mu cube, or say mu raised to the power of 4 or something else, how are you going to find? You are not going to come back to me to ask me that what is the estimator, but you have to depend on your own mind, you have to stand on your own feet, you have to depend on your own hands, that whatever is the function we can find it out. Well, I agree that these are the things where the things are very neat and clear. In case if you are working in the data science, sometimes the things becomes complicated, but surely now you have the basic concepts of all the properties, and you can use these tools in data sciences, and you can find out a good value of the unknown parameter without much difficulty, I would say. After that, it depends on your experience, on your practice, that how much practice you have made to find out the estimators of the unknown parameters under different types of conditions. Right. So, I will stop here, but I will request you that you try to take example from the book, from the assignment, and try to practice them, and I will see you in the next lecture with a new topic. Till then, goodbye.